Hi all, welcome to part 23 module 2 logic system design. So in module 2 so far we were discussing about the Boolean function, their simplification using K-map and some other related aspects, right? Now the last topic of interest is how once you have the minimized expression. So the thing is that you can have a Boolean expression say using any number of variables, but right now we know the systematical procedure to simplify it. So any bigger expression, so first task is like you simplify it. So once you simplify an expression, say f of a b c, suppose you get the minimized form as like a plus b c something. It on the original form it may be something bigger, but after you that came up and all, I simplified it something like this. Now how to implement this circuit? And the implementation, the basic idea I told you already. Something like see here, this and operation is to be done first, right? So this input b and c we will fed into an and gate. So typically we have the basic logic gates that implement the circuits. So this b and c is given to that, and suppose let me add a complement also for this a. So what I will do, so first I will use an inverter, that is a NOT gate, that will take the complement of this a. So here I will get bc, here I will get a complement. So now finally I have to OR them together, right? So I can use an OR gate, so that will give me this function. That is equal to a dash plus bc. So that is the idea. So this is this implementation part. So now we are seeing something more about the implementation. So let me tell you. So before that, regarding the gates and all, so we are already familiar with the see the gates. Say we can call them as a fundamental gates, right? Fundamental logic gates. So which are this? So gate is nothing but the basic building block of any digital circuit, right? So the internal details we are not seeing. So what we know is like we have this so-called AND gate. This is a typical notation we are having. Given two input, this AND gate will output the AND of both the inputs. That is the conjunction, right? AND operation, you know how it is working. So suppose I am giving the input like 0 and 1, this output will be 0. The AND operation, that's all. Suppose I am giving input like 1 1, it will give you 1. In another case it will give you 0. So that is the AND gate. So this is our AND gate. Now we have another fundamental gate called say OR gate. So this is the typical notation of an OR gate, right? Two inputs are given, this will give you a plus b, that is a OR. Right, so when the inputs are like 0 or 1, or operation is going to give you 1, something like that. So that is how this basic circuit is working. Similarly, we have another fundamental gate called the inverter, right? Inverter, simply this is a notation, we can call it as a NOT gate, right? So an input is given, this will just give the complement of it, a complement. So if I am applying a 1 here, I'll get a 0 here, something like that. Okay, so these three gates are known to be the fundamental gate. So why it is so? Because using them I can I can implement any. So any Boolean expression can be implemented using these three gates. So that is the first thing you have to keep in mind. So that is why we call them as a fundamental gate. So any Boolean expression, you think of it, a Boolean expression, basically it will be represented by a truth table. And from the truth table how to get the SOP, right? Using K-map, the minimal SOP or the canonical SOP, whatever it is. So any Boolean expression, so the procedure is like given any complex Boolean expression of any number of variable, right? That Boolean expression, it will have some kind of mapping, right? So that it's this Boolean expression is having a mapping given by the truth table, and this we will visualize as a K-map, and use with the help of the K-map I'll be getting minimized sum of product expression, or if I want I can convert to minimal product of some expressions, the two standard notation, so anything. So let it be the procedure. So you know the procedure how to do this, right? So once you get the minimal sum of product expression, you can so only sum of product means what? Some min terms will be there, the product term, and they are added together, right? So the product term means the literals are ANDed together. So this can be implemented with the AND gate, right? And the final sum we can implement it with the OR gate. So that's all. So this is a procedure. Whatever it is, assume that we are having some n input OR gate. Okay, if you have only two input OR gate, that you can generalize and you will get it. That's all. So that is a way. Sometimes the literals may be of the product term. So before the product term, we have the literals together making the product term. If the literal is in the original form, take it as it is. If it is in the complemented form, you say NOT gate also. So maximum these three gates are enough to implement any expression, because any expression we have a canonical SOP or a minimal SOP, whatever it is. So using anything you can implement anything. But in addition to these gates, we have many extra gates. So additional gates are like we saw many logic gates, like XOR gate is there, XOR gate, and you know how this XOR is working. So what is this XOR? A XOR B. So this is equivalent to A complement B plus B complement A. You know this XOR, you can implement it like, so this is the XOR operation, right? Hope you remember. So take this A, this is my A, and use an inverter, you will get a complement, right? Similarly, take B, use an inverter, you will get so this is our inverter, we will get a B complement. Now A and B complement, A and B complement, you have to AND together. Sorry, you have to perform the AND operation between A and B complement. This is going to give you A B complement. Similarly, this B and A complement, you can use another AND gate, that will give you B into A complement or A complement into B complement. And finally these two, you know, you can use an OR gate, and that will give you the final A XOR B as the output. So you see how bigger is a circuit. So to implement this XOR operation, and it is, you know, in many even in this parity check, like that, in many of the digital circuit, we will see this XOR gate at some point. So to implement it, this much complication is needed. But if I have a single logic gate that can do the entire thing, that is something good for me, right? So what I can do is, yeah, that about it. So if I have a single logic gate that can do this, then it will be much better for me, right? So what I can do is, I can have a logic gate, let me call it as a XOR gate. So this is a typical notation. The OR gate only, we will use one more symbol like this, so you can remember. So this is a notation we are typically using. So A and B, so the output is like some XOR, A XOR B. So you are getting it directly. So for example, if I am giving A as 0 and B as 1, you know, the XOR operation is going to give you 0 XOR 1 is 1, I think, right? So that you will get. So you don't have to worry about what happened inside the circuit and all. So like that, we have ready-made chips also, but again they can be implemented using that AND, OR and NOT gates, as they are the fundamental gates. And another one we saw already is the NOR gate. I am not explaining, XNOR gate. I am not explaining them in detail. It is something we already seen, and also you can refer the textbook about them. So it is just like here there will be a bubble, so that is a notation, and the output is like a dot round, like that. This is the way we are representing the XNOR operation. So that about it. So like that, many so this XOR and XNOR, they are somewhat important, but you know, they are not something like very important one, because without them also we can implement any logic circuit. Okay, fine. So that about it. Now another two more gates which are of interest is the NAND gate, the negation of the AND. So AND gate, you know how it is. This is our AND gate, right? So AND operation. So the inputs are just getting ANDed, and the output is like A dot B. And NAND gate is just like put a bubble over here, so that will give you the NAND operation, NAND gate, and it is typically the AND operation complement of that. So that is what we call as an AND operation, right? Similarly, we have another gate called NOR gate, and the OR gate only with a bubble in front of it. So don't confuse it with the NOT gate. inverter, because inverter is typically a triangle kind of representation we are using, something like this. And this is the representation of the OR gate with a bubble in front of it. So that is what makes the NOR gate. NOR gate, that is the OR operation, its complement, something like that. So this is, so these two gates are important, and they are more important also because let me write. So these two, NAND gate and NOR gate, they are known to be the universal gates. So they are having some relevance in that way. So they are known to be the universal gates. So why they are universal gates? This using this NAND gate alone, right? NAND gate alone. Any other logic gates can be implemented. See, this is my argument. Using NAND gate alone, I can implement any other logic gate. So this is something that makes this NAND gate special. Special in the sense I can call it as a universal gate, because it is something that NAND gate alone is enough. I don't want to produce too many number of AND gate, OR gate, NOR gate, XOR and all. So if I have a manufacturing unit which can produce only NAND gate, that itself is enough. Using them I can implement any other logic circuit. So that is the thing we are arguing. Now let's see why it is so. So my statement is like this NAND gate, using NAND gate alone I can implement any other logic gate. So is it correct? So first we have to see how to implement the fundamental gates. So if you can implement the AND operation, NOT operation and OR operation using NAND, then the statement is correct, because using AND, NOT and OR, any expression can be implemented. That we seen already, right? So the only thing, so the proof of this particular statement is something like we are trying to implement the fundamental gates using the NAND. So let's see. So the first part of the proof is like implementation of AND gate using NAND. So that is the first part. So how can I implement the AND operation using NAND? So what I have to do is the AND operation using NAND, right? So you know how this NAND is working. I think just want to tell you something. Implementation of, let's start with the NOT gate, the basic one. Okay, NOT gate using AND. So that is the first thing. So NOT gate I have to implement. So NOT gate, you know the operation, any input is given to this NOT gate, it is going to give the complement, right? It's complement. This is my NOT gate. How can I implement it using NAND? That is a question. So I am just taking a NAND gate. Then the both of the inputs, an AND gate is typically a 2 input NAND gate. It's a binary operation, right? NOT is actually a unary operation. So this is a unary operation, right? This is a binary operation, right? Binary operation. So even though it is a binary operation, both of the input I am giving to the common input, that is this A. And let's check what is the output. So what you can see is the both inputs of this NAND gates are A only. So this is going to give you A dot A the whole complement, something like this, right? A dot A the whole complement. Now hope you remember by using the idempotent law, this A dot A is nothing but A complement. See, when I am applying A, I am getting A complement as output. So this is enough. So this is how you can implement a NOT gate using a NAND gate. Hope it is clear. This is how you can implement a NOT operation using a NAND operation. Simply merge 2 inputs of the NAND gate and give to that unary input A. So that will output you A dash. Now next let's see the implementation of what called AND operation using NAND. So that is interesting. So how can I implement the AND operation, and you know how this AND is working. I am not drawing it. I am directly using NAND. I am trying to get the AND operation. So what I am doing is first I am applying A and B, and let me see what is the output of a single NAND. Single NAND will give you A dot B the whole complement, right? Now if I take one more complementation, I will get A dot B back, right? That you know, because we have the law. What is that law? A complement, the whole complement is equivalent to A. So similarly here what I applied is the law, that is A dot A is A dot A equal to A. The idempotent law is what I applied here to get this. Similarly here I am going to apply A complement, the whole complement is A. That you know, these laws everything we studied already, right? The double negation law. Now as by using that law you can see that if I am having a complement kind of thing, if I take one more complement, now to take the second level complement I can use a NOT gate, but I am not allowed to use a NOT gate. I have to use only the implementation of AND operation using only, let me write the word, only NAND. So I should use only NAND gate, using only NAND gates. So that is the thing. So how can you complement something using NAND, that we already seen, right? So just to take this input as the both inputs of the one more NAND. So you have to use two NAND gates. So first NAND will give you A dot B the whole complement, and second NAND both inputs I am giving to this A dot B the whole complement, so that this will output you A dot B. That is we seen already, because it will give you the complement. It is a NOT operator, right? So we implemented the AND operation using NAND. Hope you are able to follow this, or let's see one more example. By that it will be very much clear to you. So the next one is like the OR operation, the third one, implementation of OR operation using NAND. So this is somewhat tricky. Okay, so I will tell you the solution. You can try in your own way also. So OR operation you have to implement using the NAND gate. So that is the question. So I am just going to give you the way. So what I am going to do is, one second. So before implementing it, let me give you an observation. Just listen here. So you take a NAND gate, right? Now both of its input you complement, something like that. So if I am representing something like this, what does it mean? So typically when you are taking something like a B NAND, the output is like a dot B, right? Now the inputs itself I am bubbling. That means A, it's actually applying. So this bubbling is nothing but the negation. Negation is what is represented by this bubble, right? So here actually I am getting A complement. Here also I am getting B complement, something like that. So the inputs of this particular NAND gate is A complement and B complement, right? Now this A complement and B complement are, sorry, here it is NAND, so there is a negation. Let me tell you, just wait a second.